Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about sound level meters, the standard tool to measure overall sound levels in the field.
So let's get started. Sound level meters display or record the instantaneous OASPO, the overall sound pressure level. Very often, and without many exceptions, it reports it in dBA. We see photographs of a sound level meter here with an LCD display that reads out the dBA value of the OASPO. It has a tripod mount attachment, which is a 1/4 20 threading on the back side for tripod mounting, and an electret microphone inside. The readouts provided at the display are often reported every half second, 1 second, or 3 seconds, and this is referred to as very fast, fast, or slow. Sometimes, if only the 1/2 and 1 second increments are provided, the 1/2 is referred to as fast, and the 1 second is referred to as slow. The sound level meters contain more than just the screen and microphone. There's a microprocessor and potentially onboard storage that provides all of the calculation to convert the time recording into the instantaneous OASPO. The tripod mount is provided on the back of the casing for easy mounting. Here is our sound level meter. This would be considered a survey meter, given the price and calibration of this device. Survey meters are widely available from distributors like Amazon for a low cost, for instance, less than $50. Sound level meter, when turned on, will register the overall dBA value currently operating in a fast mode, see it at the top, which could be changed to slow. We see the slow updates about once per second. The fast updates about 2 times per second. We have A and C weighting, dBc and dBA. dBA would be more commonly used. And we have a max hold value, a light, and a record function. This unit has a mini USB output to connect this to a computer to transfer recorded files. This is the wind screen to minimize the influence of wind noise over the microphone. And here is the microphone, one view of it, and removing the covering will reveal a standard electret microphone, just like the PCB microphone that we've seen previously. So what does our sound level meter do when it is listening to the noise of a sound source? Let's take this example. We have a red Craftsman air compressor. A sound level meter and microphone are positioned next to each other. The sound level meter reports 86.5 dBA. The sound level meter generates that number first by recording the time domain of acoustic pressure. Let's use a 1 second increment, for example. The data that's shown here is taken from a microphone that's sitting right next to the sound level meter, but out of the photograph frame. Once in the time domain, we convert that acoustic pressure to the frequency domain through a Fourier transform. So our y-axis is acoustic pressure amplitude, and frequency domain is our x-axis in logarithmic scale. The sound level meter then converts that to SPL and octave band values by summing over the frequency limits. Once in octave band SPL, we convert it to A-weighted octave band results, after which we sum the total SPL to find the overall SPL value in dBA of 85 dBA. So this value results from the microphone recording adjacent to the sound level meter, and it agrees very closely within 1.5 dBA of the sound level meter. But this is the process that the sound level meter undertakes every second. There's natural variation in measurement of acoustic data. Even when we think the environment is constant, the data that we'll report from sound level meters or even laboratory grade microphones, it varies. It's due to room acoustics, environment, the HVAC, the air flow, reflections off of bodies, even holding the sound level meter. So let's anticipate between 1 to 4 decibels or dBA variation in all acoustic data. This also underscores why we never use decimals for decibels. Instead, SPLs are always rounded to integer values, and we interpret any given dB or dBA reading as having a plus or minus variation. Without apparent change of background noise, the sound levels vary, and we see this now. There are many types of sound level meters available, and which we choose to purchase and use depends on what we need it for. We probably won't need Class 0. Class 0 is only owned by institutes that calibrate Class 1, for instance, the NIST in America. Class 1 sound level meters are more commonly used in the highest of caliber laboratories. The price for these units is in the thousands of dollars. For instance, this high quality B&K Class 1 sound level meter that's shown here. Class 2 sound level meters are more down to earth in the price regime and have accuracy very close to the highest quality Class 1. Class 3 sound level meters are sometimes called survey meters. They are low cost and can be found easily within the $50 price range currently from distributors such as Amazon. They have readings that are often within plus or minus 1 or 2 decibels of Class 1 sound level meters. This might seem still like error, but given that sound sources themselves vary from around 1 to 4 decibels in any given stationary sense, this accuracy is often accurate for most noise control evaluations. Finally, we see a black foam piece at the ends of all of the microphones here for the sound level meters. These are called wind screens. They are in place to minimize the acoustic turbulence created when wind flows over the surface of the microphone. There are many sound level meter apps widely available for use on computers and cell phones. You'll need a sound level meter app for the projects that we'll undertake in this class. There are many free apps as well, even from the National Institute of Occupational Safety and Health, the Niosh in America. One thing to note, when you're using the app, make sure the phone is upside down. In other words, the microphone is on the bottom so that it is close to our mouth when we hold it up to our ear. So when we hold the microphone to take sound level readings, hold the microphone upside down so that it points to the noise. Here we'll explore 2 iOS-based versions of sound level meters. One is called Spectrum. We will go with the free version of this app. It shows the frequency content as well as overall sound level values. The sound level in dBA is shown here at the top right, with the 1/3 octave band readings shown in the moving bars. Let's see what this app registers as the background sound level. It's around 30 decibels. This is the Niosh sound level meter app, freely available from the Android App Store and from iOS App Store. It has settings to control the weighting, the rate, and other characteristics of the sound field, including calibration. Let's see what the background noise level is for this app. And let's compare this to the handheld sound level meter. We see that there's variation, approximately 3 decibels of variation from one app to the handheld meter. This shows that without exacting calibration, there's no way of knowing precisely what the sound level is. On the other hand, the relative changes of sound level registered from one device or the other device would be accurate within a certain tolerance. Our first use of a sound level meter in this course will be to assess noise insulation. Noise insulation is a measure to assess how well an enclosure or wall blocks sound from passing from a source to receiver. It is computed as the difference of SPL from before to after treatment. Take, for instance, this air compressor. Let's say that SPL sub 1 is the sound pressure level measured from this unit before an enclosure is designed and placed. Once the enclosure is in place, the new sound pressure level is SPL sub 2, so that the noise insulation in I is SPL sub 1 minus SPL sub 2, which would be reported in dB or dBA depending on how the SPL 1 and 2 values are reported. We also do not need to enclose the noise source entirely to calculate noise insulation. Noise insulation is a very practical way of assessing success of a new noise control remedy. So let's summarize what we've learned. We've learned that sound level meters are an industry standard tool to measure and report OA, SPL, and dBA. And sounds naturally vary in level over a few dB, which encourages us to consider any sound level reading as being within some plus and minus range of dB or dBA. Finally, noise insulation helps us assess the before and after effect of new sound level treatments, and it is a characteristic of how well an enclosure or wall blocks the sound level.
That's it for this video. Now that we've learned all about wave propagation, the methods to measure sound, and report sound levels, in the next video we'll put all of this together to learn about the basics of engineering noise control methodology.